Okay, in this video, we're going to investigate the what we call rotational kinematics, and this is the idea of looking at the position, speed, and acceleration of an object that is rotating. In the previous video, we saw what leads to rotation, that is when you have an unbalanced torque. But now we want to investigate now, if we know that an object is rotating, we want to look at what are the sort of equations that describe this. In order to do this, I've got some snapshots here of the exact same demo that we saw before. All right, and this was the one with a large disk that's rotating, but now there's a mass hanging from it. It's rotating. But what's different here is this is all from the same trial, but this is at different times. So I'm going to call this T0, T1, and T2. So this is just three different snapshots of the exact same trial. And what we'd say is, what I want to look at is what is the angular position and things associated with the angular position of this red thing as it goes around. So, right, you see it, how it's kind of like clearly going around. Okay, I'll make that more explicit in a second. But let's say at t equals 0, that was the point when I had just released it. And so it was right here. It kind of corresponded to that line. So let's call this position theta equals 0. All right, and I'm just going to re-sketch that on here. Every single one is going to be, this is the same, theta equals 0. All right, and here it looked like that. Okay, so this is kind of the position where it started, the angular position it started. Now, here you can't really see it because where it started is literally behind the blue line that I drew. But if you look over here at T1, after some amount of time, it's no longer there. The red thing on the disk has moved. So it has rotated. It has gone through this angle. In the amount of time between these two snapshots, this disk has rotated, and it's now at theta, we'll call it theta of T1. All right? And then over here, by the time we get to T3, it is all the way up here at theta of T3. Okay? So clearly, its angular position is changing. And so we're going to have some equations where we say theta equals theta 0, da 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 da. All right? And what we're going to mean is literally the angular position. Where is it? Is it right here at theta equals 0? Or is it over here at some other larger angle? Or is it up here at some yet larger angle still? Hopefully you can picture this from having watched the videos, and you can kind of put these snapshots together to visualize the fact that this theta is actually changing as time goes on. All right, and so that's going to be something that we talk about in one of these equations, but this is just a visualization of that. Now, additionally, when we were doing this demo, we saw that there was this graph down here. Okay, and on this graph, what this graph was showing was the angular speed as a function of time. And I'm going to blow that up, at least sketch it larger in a second. But for now, what we saw, roughly speaking, was on the first snapshot at t equals 0, if we looked at the graph, it's hard to see here, but roughly speaking, what it did was it was something like that. This was at t0. And then as time went on, we still had our data point down here at t0, but then we had another data point up here. So this was t0, and we had this other data point here at t1. And then later at t2, we still had our data point at t0, we had t1, and now we had this third data point up here. So this was t0, this was t1, and over here was t2. Okay. And if you remember from the video, at least at this point, while the brick was falling and there was a tension, these points all were along a straight line. Okay, so let me blow that up here, that is, make a bigger sketch. So here, all I'm sketching is my own version of the data that we saw on these plots. Okay, so again, the plot is omega versus time, and Omega is the rotational speed. So it's just a thing that quantifies how fast this big wheel is rotating around. And what we saw was that it kind of, let me put it in a different color. It kind of did this, and then this, and then this, and then if we looked at a later T4, it would look like that. And so it looked like this. It was a straight line. Okay, so now we know that this thing we saw before, or we remember from math, that this thing has a slope, which is equal to delta omega over delta t, right? It's just a rise over the run. Fantastic. Now also, from this, we can see that it's a straight line, and so we remember the equation for a straight line was y equals mx plus b, all right? Here we're going to change that because on our vertical axis, we now have omega, all right, equals, well, our horizontal axis, so in the sort of standard math equation, we're going to translate that into what we see here. So y becomes omega. Our horizontal axis, which is no longer x, our horizontal axis here is time. So this is t. The slope, we just wrote that right here. The slope is omega over delta t. So this is delta omega over delta t. And then I guess for our part, it kind of looks like 0, but in general, this doesn't always have to be 0. It could have started with some initial angular speed, so that is going to be our y-intercept. Okay, so that is really just taking what we know from math, the equation for a straight line, and rewriting it in terms of variables of our graph that we saw from this demo. All right? And so when we do that, let me just rewrite this. This is omega is, I'm going to make it a little bit clearer. Okay, now something that we saw in the video when we were talking about Newton's second law was that delta omega over delta t, all right? Clearly that's the slope of this line, but what this means is it's the change in speed with respect to time. And we saw this before, very beginning of the semester, when we talked about a change in speed with respect to time, we talked about delta v over delta t. We called that the acceleration. Well, we have the exact same thing here, but rather than being the sort of regular, like acceleration a, here we're talking about something going around in a circle. And so this is going to be the change in angular speed with respect to time is what we're going to call alpha. And this is the angular acceleration. All right. And this was actually the exact same thing that we saw show up in Newton's second law. All right, Newton's second law for rotations. So if I use that, then our equation becomes omega is alpha t plus omega 0. Okay, great. That is, that's really just something that we kind of read straight off of that graph from the demo that we did. Now, notice, this is a speed. It's an angular speed. This is an acceleration. I guess it's an angular acceleration. I don't need the parentheses. It's the angular acceleration. And I guess this is the initial angular speed. Okay? Right, and again, and this is the time. Okay, nice. If we kind of remember back to when we were first starting the semester, we had an equation that said the speed was AT plus V0. Notice how this equation, this is the speed, this is the acceleration, this is the initial speed, and this is the time. Notice how this equation this equation here that we're kind of comfortable with now, it looks almost identical to that equation we just derived, right? And that is this equation that we just derived from this demonstration. It's going to turn out that that is something that is going to be that we can do in general. Now, I'm not going to derive them here, but all of our equations that we used for kinematics, we are going to be able to have exact corollaries for rotational kinematics. All right, and I think I've got them written down there, but so the first one we had V equals, let me rewrite as V0 plus, V was AT plus V0. And we saw that there was this, when we looked at rotations, the thing we just derived was omega was alpha t plus omega 0. The direct rotational correlation to this equation that we knew before. All right. Well, it turns out, like I said, there are exact correlations for all of our kinematic equations. You might remember that there was x equals x0 plus v0x times t plus 1/2 at squared. Well, what would the angular correlation be? Well, I guess let's start here, because we know that a became alpha, and we know that v0 became omega 0. So we've got something equals something plus omega 0t plus 1/2 alpha t squared. Now the question is, what is it that plays the role of x? Remember, x was the position of the object that was moving. All right? Well, if we look at our rotational analogy, what plays the role of position is this theta. It is the angular position. And so everywhere in our previous equations where we had x, we can replace it by theta. So theta equals theta 0 plus omega 0t plus 1/2 alpha t squared. Let me make it clear. That's 1/2. Okay? So again, same kind of thing. And then I guess the final equation that we really used was v squared is v0x squared plus 2a x minus x0. Doing the exact same translation, what we would get is omega squared is omega 0 squared plus 2 alpha theta minus theta 0. All right. And so now we have this new set of equations that are really just kind of translation. They're just kind of interpreting our kinematic equations that we became comfortable with. We're translating them into the equations that we would use when an object is rotating. Okay, and this set of equations are the set of equations that we are going to be able to use to analyze the motion of objects as they're rotating, whether it's the position, the speed, or the acceleration. Okay, and so this is the stuff that I had before. So let me just bring this up here, and we will be, that's the description of what each of those variables mean. Okay, so these are the concepts and equations that you're going to explore as you start to do problems that involve things rotating.